Welcome back to this explainer. Today, we are looking right at the Cambridge Physics 9702 syllabus, specifically unlocking the absolute secrets behind alternating currents and root mean square, or RMS values. Look, if you've ever walked out of an exam feeling like you truly understood the physics, like you really nailed it, but then somehow didn't get the marks you expected on results day, you are exactly in the right place. Today, we're not just reviewing formulas, we are peering directly into the examiner's mind to see exactly what they are looking for when grading this specific topic. Our goal is to help you design your answer like a master architect, where every single calculation and paragraph is a structural masterpiece. And hey, before we dive into the deep end, make sure to subscribe to our YouTube channel, AC Exams, at acexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's kick things off by asking a crucial question, one that honestly separates the top-tier students from the rest of the pack. Why do students consistently lose easy marks on AC R.m.s questions? Think of two classic types of students. Let's call them Alex and Sam. Alex overloads every answer with raw physics facts, but provides absolutely zero analysis. Sam, on the other hand, rushes the math and completely misses the specific requirements of the command words. The principal examiner reports actually highlight this constantly. It's rarely because you don't know the basic physics. It's all about execution, methodology, and how effectively you communicate your underlying analytical process on the page.
So, to fix this, we are going to deconstruct this entire topic like a principal examiner would. We'll be moving through 5 critical stages today: core concepts, the analytical framework, technical methodology, critical analysis skills, and finally, the top examiner warnings.
Let's jump right into Section 1, Core Concepts, the theoretical architecture.
Right, before we can even think about solving complex exam problems, we have to establish the absolute core principles of alternating currents that the syllabus demands. The crucial point here is knowing these fundamental formulas inside out. They translate peak current and peak voltage into their root mean square equivalents. So you've got current RMS equals the peak current, that's the I naught, divided by the square root of 2. And similarly, the voltage RMS is equal to the peak voltage divided by the square root of 2. You absolutely have to commit these to memory. But, quick warning here, a super common mistake students make when the clock is ticking and they're under pressure is misapplying that square root of 2. For instance, they'll divide the RMS value by it instead of multiplying to find the peak. So take a moment to really lock in the correct causal relationship. The Cambridge Assessment Framework prioritizes analytical depth over superficial breadth. So just memorizing these equations isn't going to cut it. You need to understand the systematic analysis behind them.
What's really fascinating here is that examiners specifically note that candidates who reference cross-topic connections achieve significantly higher marks. It's not just about the formulas, It's about the theoretical architecture resting on precise definitions and causal relationships. Ask yourself, how does this AC current actually generate power? How does it link to other areas of the syllabus, like electromagnetism? When you integrate your knowledge across the entire physics syllabus, you're literally signaling to the examiner that you have a master-level grasp of the subject.
Moving smoothly on to Section 2, the analytical framework, thinking like an examiner.
Let's look at the overarching mental model you need to adopt the second you open that exam paper. Look, the highest scoring students don't just jump straight into the math. They use a very specific framework called the deconstruct, solve, evaluate mental model. This specific framework is how you should approach every single complex physics problem you ever encounter. It forces you to slow down your initial panicked reaction and structure your reasoning logically. This perfectly aligns with the distinct cognitive domains the examiners are testing: knowledge, application, and analysis. So, instead of just blindly plugging numbers into the RMS equations, break down your problem-solving process. Step 1, identify the given information. Extract exactly what they're telling you. Step 2, break the problem into logical steps. Step 3, solve systematically. Step 4, and actually, scratch that, this is probably the most important one, check for reasonableness. Does your calculated RMS value actually make sense in the context of the peak value given? And finally, Step 5, make justified recommendations based on your findings. Now, before we move to the next phase of our framework, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's keep the momentum going with Section 3, Technical Methodology, the Standardized Sequence. Let's see how this builds into the specific procedural framework demanded by examiners. It's all about how you physically handle the data that's thrown at you. Data interpretation skills are absolutely critical here. Imagine a 60-second timer on your screen during an exam. You must actively extract data from complex texts and tables under that pressure. Superficial readings, they will immediately cost you marks. You need to interpret the relationships presented to you. Maybe it's the relationship between time and voltage in an oscillating AC graph, and then draw solid, evidence-based conclusions before your finger even touches a calculator button. When tackling these specific exam questions, you absolutely must follow this standardized sequence from identification to formal presentation. First, identify the key elements. Second, apply the relevant theoretical principles. Third, execute your analysis with exceptionally clear working. Fourth, verify your results. And fifth, present them in the appropriate format with the correct terminology. If you miss that final step, say you forget the units or format it poorly, you are throwing away all the hard work you just did on the calculation. Now we enter the fourth phase, critical analysis skills, earning the high marks. This is where we focus on those higher-order assessment objectives that secure the A stars. Often, you'll be asked to evaluate different approaches or compare datasets. But here's the thing. Comparative analysis isn't just about pointing out what matches. You must use comparative connectives to highlight differences and support every single comparison with hard evidence from the question itself. Then, you need to draw conclusions about their relative importance. This shows the examiner you aren't just reciting a textbook, but truly analyzing the physics at play. Furthermore, if you want to demonstrate true analytical depth, you have to explicitly evaluate the quality of the evidence. You need to identify the limitations of the data provided, explicitly state the assumptions made in your Ir.m.s calculations. Like, are you assuming it's a perfectly ideal sinusoidal wave? You have to state that. Consider alternative interpretations and assess how these factors impact your final conclusions. This level of evaluation is exactly what the descriptive, analytical, and evaluative levels of the marking framework demand from top candidates.
Finally, let's move to Section 5, Top Examiner Warnings, the Method Mark Strategy.
Let's dive into the actual principal examiner reports to see exactly where students consistently hit a wall. This is arguably the most important takeaway of this entire explainer. Listen closely to this direct examiner alert. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Wow. Your process is literally just as important as your final mathematical answer. If you make a tiny, silly calculator error on an R.M.s calculation, but you have laid out a flawless, deconstruct, solve, evaluate methodology on the page, the examiner can still award you the vast majority of the points through method marks. Never leave the page blank and never hide your workings.
Memorize these 3 classic traps pulled directly from the examiner reports. Number 1, the wrong approach, using an incorrect methodology for the specific AC context given. Number 2, formatting errors, doing all the incredibly hard math, but forgetting to check your final presentation in units. And number 3, lacking specificity, providing generic, memorized physics answers that aren't actually tailored to the specific context of the question. You have to answer the question in front of you, not the one you wish you had been asked. So, as we wrap up this explainer, I want to leave you with a challenge. Before you sit down to practice your next set of physics questions, ask yourself, how will you actively change your study habits based on these examiner insights? Will you slow down? Will you show every single step of your working to secure those method marks? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. The blueprint is in your hands now. Happy studying.